Should be good. Okay, so make sure you have your iClicker ready, and then you actually do need a pen or pencil. Any kind of writing utensil. Please make sure your masks are covering your nose and your mouth. Thank you. Few minutes. Any questions? Pearson site working? So. I know we're still working on a few problems. At least it was better than it was this weekend. I think every day I've either been on the phone with the bookstore, the Pearson rep, the Moodle person, like, you know, but it's just that nobody knew how this integration was going to happen, you know. So we're just figuring it out. It'll be better next semester. Will always be better next semester. So don't forget to go ahead and put in your name on the seating chart. I really appreciate y'all doing the seating chart every day. We get into the habit and just do it. Got a few minutes still. All right, so everybody got a pen or pencil, something to write with? And then make sure your iClicker's ready, because that's the second thing we're gonna do. So y'all remember at the very beginning of the semester, I had y'all do something for me. I'm gonna ask y'all the same question. Draw and label a water molecule. I'm not grading it. I'm not grading it, but I want you to use what you have learned and draw now what you think a water molecule looks like. So draw and label a water molecule. When you're done, turn it over. Don't let your neighbors look. This is not a sharing activity. I want to know about each of you, not about your neighbor, okay? So I'm going to give the front row enough papers to pass back to the back, okay? So I'm coming around with that. If there are any extras in the back, I'll catch them again. Get your N number off of somewhere, just get it. Okay, so who's on, let's see if anybody on Zoom who's not in the class. So if you just want to do it, it's just draw and label a water molecule and then take a picture of it and email it to me. And that'd be great. Everybody got one? They need one? And just make sure your mouths are coming in nose and mouth. When you're done, just flip it over. And I can see. A noodle or a banner. Banner. Yeah, it isn't much of the corners. And banner. Probably is. You'll need that for the exam. Y'all, for the next exam, you will need to have your N number. So make sure you come knowing your N number. Was it on it? If you go to the banner, so they go to mine, and then click banner. And you log in, it should be in the upper left or right. Keep finding it, but everybody else passing up? You guys need time? They're passing up? Okay, do you feel more confident about that this go round? A little bit more, hopefully a little bit more. Okay, so take out your iClickers. That's our next thing. Take out your iClickers. I'm gonna do a couple of questions. Okay. Oh, did I save what I wrote on them? Oh, come on. Okay, that's fine. We're gonna do. I so did. How do I not do that? Oh no. Let's see. Can I clear? Let's see. Can I undo all writing? Oh, don't look, y'all. Close your eyes. Let's see. Did it take it all? I think it did. Okay. We'll try this. All right. Let's skip that one. All right. All right. Here we go. So what kind of bonding arrangement is found in an alkene? An alkene. Click in on your own. Oh, I didn't click it. Okay, there we go. Remember, you have 1 minute to click in. Okay. So talk to your partners, talk to the people around you, just come up with another chance to click in. Okay, 30 seconds, so 10 seconds left. Click in your second answer. Make sure you click in for the second time. Okay. So what did we say? Good. Let's see if I can grade it. All right, so we definitely went up on that one. We definitely went up. So now that everybody knows that we have an alkene in answer number C, this is an alkene. Why is it an alkene? E-N-E. E-N-E for the double bond. Okay, tell me about A. Alkane. Tell me about B. Alkyne. And tell me about D. Cyclo. Alkane. A-N-E. Yeah? Okay. All right. What is the name of an unbranched hydrocarbon with the formula C5H12? C5H12. Remember, 1 minute. Ten seconds. Okay, turn and look at people around you, talk to people, click in again. Looks like almost everybody's responded already. I'll give y'all till 30 seconds. Make sure you get that second response in. 5 seconds. Make sure you click in again. All right. So what do we say? Okay, so if we look at this, C5, what is 5? What's the prefix for 5? Pent. Now, because it's a 12, what do I know about this? It's a straight chain. It's not a ring, right? Because it fits the formula CnH2n plus 2, because we need those extra 2 hydrogens for the N carbons. So this must be pentane. What if I told you it was C5H10? What would you call it? Cyclopentane, right? So this one was easy because what did I give you for the ending for all of them? A and E. And what are you going to have on the exam? Your best friend. And what's your best friend have? Those covalent prefixes. And the only ones that are different are the first 4, which are methyl, ethyl, propyl, butyl. Okay, so you have to know them. All right, and you could have drawn it, you know, sometimes drawing it makes it easier to name too, but you don't have to. Okay, what is the name of the saturated unbranched hydrocarbon with this formula, C6H12? Okay, about 10 seconds left. All right, turn and talk to your people. Click in, don't forget to click in again. Easier when it's stuff we've covered already, isn't it? Yeah. Okay, 5 seconds. Make sure you've clicked in again. I thought we had more than 43. Okay, so what did y'all say? All right, so did we go up? Very nice. Okay, so why did you pick cyclohexane? The only reason that you know that it's an ANE instead of an ENE is what? Because we said saturated. If we had said unsaturated, then it would have to either have a double bond or a triple bond inside of it. But because we said saturated, we know that it is a single bond. So we know that we have all carbon single bonds, and then each of those carbons has a hydrogen attached because it's saturated. And then we know it's a ring because it fits the CnH2n. Don't add the extra 2 formula, right? Okay, good, very nice, very nice. Did y'all see I posted iClicker grades too? I pulled your iClicker grades today, this morning. I posted those too. So whatever your iClicker score is, your percentage score, you add 20 points to that, and that's your iClicker score on Moodle, right? Because remember I said 70% is the lowest A. So you take your iClicker score and add 20. Okay, so the last little section we have to talk about in organic compounds is isomerization. So molecules can be very similar in a couple of different ways. So you can have something that is called a conformational isomer. In a conformational isomer, this is what I like to make an analogy to. A person like myself, if I did the YMCA, which is fun to do, right? When I'm doing this, do I change?
arm come off and move or no, right? So I'm changing my conformation, right? But am I the same molecule? Absolutely, absolutely. That's a conformational molecule. So I could take the molecule, any molecule that I have, right? And I can rotate it in 3 dimensions. I can move, I can rotate bonds, you know, I can turn things. And it's still the same molecule, right? Okay, the other thing that can happen is that you can have what are called structural isomers. If you took me and you detached one of my arms and detached one of my legs and flipped them and put my leg where my arm is and my arm where my leg is, would I still be made of the same stuff? Yes, I'd still have the same number of carbons, the same number of hydrogens, but would I be the same? No, that's a structural isomer. So structurally, I would be built very different, right? That'd be really weird. But that's your difference there. A structural, the molecular formula is the same number of carbons, same number of hydrogens, but the atoms are connected in a different way, right? So my arms and legs are connected in a different way. And then the third option is that they're not related, right? So no matter what, if you're an isomer, you have the same molecular formula. If you don't have the same molecular formula, you are not an isomer, right? So let's go look at some examples. All right, so we have to determine the relationship between each of the pairs of the following compounds. Are they structural isomers, conformational isomers, or not related? So what should you do when you're looking at these problems? What's the first thing Dr. B always tells you to do? Count your carbons, count your carbons. So I'm going to count my carbons on the first molecule. I count my carbons on the second molecule. Do I have the same number of carbons? Yeah. Okay, so then I can say that most likely this is going to be an isomer, right? But I need to figure out what kind of an isomer is it. So what do we think? Structural or conformational? Why? That's right, conformational, because it's the same molecule, you're just drawing it 2 different ways, right? One's a skeletal diagram, one's a condensed structural formula. Doesn't really matter, right? I could have taken this and I could have drawn it this way. 1, 2, 3, 4, erase that one. Okay. And I still have I'm trying to count 1, 2, 3, 4 carbons. It's the same molecule, right? So this is a conformational isomer. Let me ask you a quick question. How would I name the molecule on the left? The first molecule. Me eat peanut butter, butane. How would I name the second molecule? Conformational isomers have the same name. They might look different, but if you get down to the nitty-gritty and you name them, they're going to have the same name. Okay, look at B. What do you notice about B? Well, they're both cyclo. They're both cyclo. So if I were to number this, 2, 3, 4, 5, 1, 2, 3, 4, 5, it's the same number of members in the ring. But what's different? I have a methyl, and then on the second molecule, I have a methyl and an ethyl. So what would happen to my number of carbons? How many carbons in the first molecule? So I have 7 carbons. How many do I have in the second molecule? 8 carbons. Do I have the same molecular formula? No, because this one's going to start C7. This one's going to start C8. Doesn't even matter what the H's are because the carbons aren't the same. So if you don't have the same molecular formula, are you an isomer? No. So are we a conformational isomer? No. Are we a structural isomer? No. So what do we write? Not related. Okay. If we were to name it, would they have the same name? What will we name the first one? Cyclo, so yeah, we would have a cyclo. CYCLO. And there's 5, so it would be cyclo, pent, and then single bonds, ane. And what else would we say? 1,4 dimethyl cyclopentane. How would we name the other one? One ethyl, 4 methyl. Did you see how I numbered that correctly for y'all? THYL. And then what? Cyclopentane. They're not going to have the same name. If it's not related, it's absolutely not going to have the same name. But I thought that was just a good opportunity to name it, right? Just fun. Just fun. Okay. C. I'm going to say I want to count my carbons. So on my first molecule, do I start at the top, in the middle, or at the bottom when I count? Or do I start on the other end? There are lots of options. You could either start at this end. Could you? Well, no, you can't. Could you start at this end? No. You have to either start with the one going up or the one going down. You can't start in the middle because we're looking for our longest continuous chain of carbons. Does it have to be continuous from left to right? No. It's like if you put your finger on the carbon, if you can keep your finger without having to raise it up, that's your longest continuous chain, right? So you'll want to start up or down? Down. Okay, so 1, 2, 3, 4. And then what do I have coming off of carbon 2? A methyl group. Okay, so now here, do I start up or down? It doesn't honestly matter. You could start with either carbon. You couldn't start with this carbon, but you could start with either one of these. So let's do this. 1, 2, 3, 4. And then coming off of carbon 2, what do I have? A methyl group. So how would I name the first molecule? Two methyl. TH, 2 methyl what? Me eat peanut butter. Butyl, but, and then A. 2 methyl butane. How would I name the second molecule? 2 methyl butane. Sometimes naming it just. Okay, so what do I call this? Structural isomer, conformational isomer, not related. Conformational. Yeah. Sometimes naming it really, really helps. Okay, D. Do I start here, the front, or do I start at the back? Doesn't actually matter. 1, 2, 3, 4. Do I stop there? No, because I can put my finger and I can continuously, and I'm still continuous. So there's 5 carbons in that chain, in that parent chain. Do I have anything coming off of the parent chain? No. Typically, we draw it coming down this way, but doesn't have to. Okay, do I start down, up, or at the end? You could either start up or you could start down, but you can't start at the end. So 1, 2, 3, 4. And on my second carbon, I have a methyl. So name this first molecule. Pentene. The pentane. How do I name the second molecule? Butane. So are they structural isomers or conformational isomers? or neither? Well, how many carbons are in pentane? C5, and then it fits the formula H12, right? Okay, so how many carbons are in 2-methylbutane? 5, because you have to count that methyl. There's 4 in the parent and there's 5. C5. How many hydrogens? 3 here. How many here? 1. So that's 4. 3 here. It's the same number. It's just because this one lost a hydrogen and this one gained a hydrogen, right? So it's still H12. So it is structural isomer. Okay, how about E? What should we do? Should we count our carbons? I'm going to say that's a waste of time. I don't normally say that, do I? Why is that a waste of time? If I'm going to write the formula for this, right? I'm going to have a certain number of carbons. I'm going to have a certain number of hydrogens and a certain number of what? Bromines. If I write it for the second molecule, I'll have a certain number of carbons, a certain number of hydrogens, and a certain number of chlorines. Can my molecular formula be the same? No. So am I an isomer? No. So these are not related. If you ever see that, like 2 completely different atoms, automatically not related. Sometimes test taking skills like that save you time. So that's a really important thing to be able to do. To know when to spend a lot of time on it and when not to. Okay. So the next thing that we're going to talk about in terms of how molecules can arrange themselves in 3 dimensions, right? Because that's kind of what we were talking about, is if you have a ring, if you have a double bond or a triple bond. So if you have a double bond, triple bond, or a ring, you can have things that are cis or trans. So if we have something that, for example, has a double bond. So do y'all see these 2 carbons? Do you see I have 2 things attached to them here? So instead of having 1 bond between the carbons, I have 2. Okay. You look at where that carbon-carbon double bond is. And you look at what's attached to these 2 carbons. So if I select this carbon here, I have a hydrogen, and then I have an R group, right? For what does R stand for? Rest of the molecule, right? We don't really care what it is, but we have an R group here. And it is it going up or is it going down? It's going up, which means it's above the plane of the double bond. So this is the plane of the double bond, it's higher. The hydrogen is going what? Down. Okay, so look at your second carbon. I have a hydrogen, the hydrogen is going up or down? Down. My R group, it's different, it has 3 carbons in it, but it's still an R group, is going up or down? Up. Okay. When we talk about if something is cis or trans, the thing with a double bond, a triple bond, or a ring is that I can't rotate about the bond. I can do it if I have a single bond. Do you see how I can rotate that? It can go any which way it wants. Any single bond can do that. But a double bond, I can't. And it's not just physically like this, it actually is chemically like that. You can't actually rotate about a double bond, a triple bond, or a ring. And so what you have to say is what's happening with these R groups? Are they both in the same orientation? So if I do this, they're both what? They're both up. If I do this, they're both what? Down. So I don't want to say up and down. I want to say, are they on the same side or are they on different sides? So it doesn't matter if they're both down or both up, they're both on the same side. So if they are both up or down, it's the R group, we call that cis. So my little mnemonic for that is same side cis. You hear the S and everything? I know it's a C, but it sounds like an S. Same side cis. Okay, I cannot rotate this. So what I'm actually going to have to do in order to show you the other isomer is to actually take the groups off and reposition them. Okay, now I have my carbon-carbon double bond. On the first carbon is the group going up or down? Up. On the second carbon is the group going up or down? Down. Now I can rotate this in 3 dimensions. And now the first group is going down and the second group is going up. But they're always going to be opposite of one another. One goes up, one goes down. So our groups are opposite. We call that trans. And have you heard transatlantic? Right, if you take a transatlantic flight, you're going to go across the ocean. So across. Right, so you have to go across. One's going to be up, one's going to be down. You have to go across, right? So that's why they call them cis and trans. So these are other examples of isomers, and we call these stereoisomers. Okay, so we can draw them in a cis or in a trans orientation. Now this is 3-dimensional. This is really nice. But on paper, do you have 3 dimensions? Nope. So we're going to have to remember our rules for drawing in 3 dimensions. Do you remember that? So if something's coming towards you, well, towards you, what will we draw? The solid. If it's coming behind the paper, away from you, you do the dash thing. Okay. So can I erase this? Because I don't really have a whole lot of room. Make sure you've jotted that down. Okay. I took up all my space with that. Okay, so we're looking for a double bond, a triple bond, or a ring. Do we have one of those things in A? Yes, we do. Okay, so if we have this ring, we're looking for the R groups that are coming off the ring. So where are my R groups that are coming off the ring? If I number my carbons, what do I have? On carbon 1, I have a what? On carbon 1, I have an ethyl. On carbon 3, I have a methyl. M-E-T-H-Y-L. I'll put an extra L. Whatever. Okay. So I'm going to draw my ring. Right? It's the little house. I want to draw my methyl going one way and my ethyl going the other way. So if I draw my methyl as a solid, how do I need to draw my ethyl? As that dashed, that weird dashed thing, right? That gets bigger as you get farther away. But if I leave it like this, I have 2 methyl groups. So what do I need to do? Add my second carbon in the ethyl, and you can just do that with a line because you already know that it's going away from you. So what have I drawn here? The cis or the trans orientation? Trans. Okay, so how do I draw the cis? There are actually 2 ways that I could do it. Let's do both of them. That's terrible, but it's okay. How would I do it? If I drew this one the same way, if I drew it as a solid, how would I make this the cis configuration? Do the other one the same way. Cis is the same, right? And then just draw a stick coming out of it. What's the other way to draw cis? Both of them as dashed lines. Both of them are cis. So there's always going to be 2 ways to draw cis, 1 way to draw. Well, you could actually do the other way to draw trans. You could draw
right? This one could be, come on, like this. And then this one would be your colored in. So this is also trans, right? But you only have to be able to do one of each. Okay, look at B. What do you notice about B? In B, I have two things coming off of the ring. Let's see if I can make this real quick. It's not quite perfect, but I have a ring here. Y'all see that? I have a ring here. And coming off of that ring, I have two groups. I have one group here, I have one group here, okay? How do I have a cis and trans orientation with this? Always one's going to be up and one's going to be down, right? Can I reposition them? If I took this one off and took that one off and repositioned them, it'd still be one up and one down. So if they're on the same atom, there's no cis or trans. All you do is this, right? And then it's a, what kind of an isomer? Conformational or structural? Conformational. Then it's just a conformational isomer. So you can have a conformational isomer here, but you cannot have a stereo isomer. So it is not possible. Because the R groups are on the same atom. Right? One's always going to be up, one's always going to be down. So you'll never have cis. Okay, look at C. What do we have in C? Do we have a ring? Or we have a double bond? We have a double bond. So what I like to do is I like to redraw the molecule, but redraw it in so that I can see a little bit of the structure, right? So I always draw my double bond being flat so I can see up and down. So let's number these. 1, 2, 3, 4, 5. And then I have a methyl group coming off of 4. Okay, so here's carbon 1, here's carbon 2. What's attached to carbon 1? Hydrogens, 2 hydrogens. So what I'm going to do is I'm going to go 1 up, and I'm going to go 1 down. Right? Because it doesn't, 2 hydrogens. Look at carbon 2. What's attached to carbon 2? The rest of the molecule and a hydrogen. Remember, carbon needs 4 bonds. So I didn't draw all this. I just said all of this is R. Y'all see that? Okay. So in order to have a cis and trans configuration, I have to have R groups that are on opposite sides of the double bond. Do I have R groups that are on opposite sides of the double bond? No, I only have 1 R group. So can I have a cis and trans configuration? No. So this one is not possible because I only have 1 R group, because there is only one R group.
How do you know that like A is not cis? If you can draw it.
Wait, how do I know that A?
Yeah.
Go back up to A. This one?
Yes.
Okay, ask me again.
Like we put our answer as trans, but like why is it not cis? Because you could draw it cis like cis too.
Well, yeah, here, these 2 are trans, these 2 are cis.
Oh, okay. Never mind.
Okay.
Yeah.
All right. So we can't draw C as cis or trans because there's only 1 R group. We would need 1 R group on this carbon, and then one of these 2 hydrogens would have to be an R group. Okay, so let's try D. Everybody okay on C?
Okay, so let's draw D. So what I do is I number my carbons. And I'm going to draw what I really want to focus on. What do I want to focus on? My double bond. So I'm going to have, this is carbon 2 that's double bonded to carbon 1. What's attached to carbon 1? A hydrogen and a fluorine. Okay, what's attached to carbon 2? The rest of the molecule. So I'm going to do this. I'm going to say that's R and a hydrogen. Okay, what did I draw? If I have one R group here, what's F really? It's another R group. It's another R group. So what did I draw? Trans. Because they're on opposite sides of the double bond. So if you draw basically a dashed line that goes through the double bond, you can see that one R is above and one R is below, right? So let's draw the other configuration. So I have carbon 1, carbon 2. Here's a hydrogen. Oh, well, that's fine. Let's do that. Here's a hydrogen, here's a fluorine. What do I do differently for this carbon? I put the rest going down and I put the hydrogen going up. So I look at my R group here, I look at my R group here, and they're both, here's the plane, they're both below the double bond. So this is what? Cis. How else could I have drawn cis? As both above. How else could I have drawn trans? With the F up and the R down. Right? So really multiple ways to do that. Okay. All right. The last thing that we're going to talk about are chiral centers. All right. So you can have some molecules that have the same molecular formula. That's an isomer, right? They have the same connectivity. So what do we normally call that? If you have the same connectivity, means your structure is the same. So are you a structural isomer? No, you're a conformational isomer, right? But they're unique because they're non-superimposable. So, right, look at your hands. Your hands. They're mirror images of one another, right? So you can have molecules that have the same connectivity, right? The same number of R groups and stuff like that. And they're mirror images, but they're non-superimposable. So when I try to superimpose my hands upon each other, what happens? My thumbs don't line up, right? So the same thing is true about carbons that have, see if I can do this real quick, that have 4 different groups attached to them. Oh, that's got a broken one. Oh. These things are getting so old. Start pulling them and they start breaking, right? So if I have a carbon that has 4 different things attached to it, if I had another one, I could position my 4 so that I have 4 different things around it, but they would be non-superimposable. They wouldn't line up when I laid them one on top of the other. So this only works. This only works in chiral, things that are chiral. So in order for something in chemistry to be chiral, you have to have what molecular shape? What shape is that? I thought I heard it. Tetrahedral. So you have to have a carbon that is tetrahedral. T-E-T. But not just tetrahedral. What if you had something that was tetrahedral but with 4 hydrogens attached to it? Well, I could superimpose that, right? 4 hydrogens, doesn't matter what orientation, I can superimpose that. So it has to be a carbon that is tetrahedral with 4 different groups attached to it. And so we call molecules that have chirality, we call them a particular kind of isomer. We call these, they're a type of stereoisomer, and they're an enantiomer. E-N-A-N-T-I-O-M-E-R, enantiomers. So if you have two molecules that have the same connectivity and they're mirror images of one another, but they're non-superimposable, they are enantiomers. Okay, so these are non-superimposable mirror images. And so enantiomers have chiral centers. So enantiomers have chiral centers. So if you want to know if a molecule is going to be able to have an enantiomer or not, you need to look for chiral centers. So let's practice looking for chiral centers. Can it be any atom that's chiral? No, what does it have to be? A carbon that's tetrahedral with 4 different groups attached. So none of the oxygens can be chiral. So let's just look at carbons. This first carbon up here at the top, is it tetrahedral? Well, it's bound to 2 hydrogens, an oxygen, and another carbon. So it is tetrahedral. It's got 4 things attached to it, but is it 4 different things? No, it's not. So I'm going to draw a red X on it. I'm going to cross it out. It's not chiral. So let's cross this out. Let's not put an asterisk because that's going to get confusing. Let's circle them. Circle the chiral centers. Okay. So let's go down to the next carbon. Tell me about this carbon. What's attached to this carbon? I have an oxygen that's attached to it. And the oxygen basically in like that side of the ring. Okay, so that's one. Then I have another R group that's that side of the molecule. It's not the same, it's different. And then I have this R group. So that's 3. Do I only have 3 things bound? I have a hydrogen. So do I have 4 different things attached to this carbon? Yes, I do. So do I have a chiral center? Yes. Okay. The next carbon down. Chiral or achiral? A meaning absence of. So I have an oxygen and a hydroxyl, right? Then I have this portion of the molecule, and then I have this portion of the molecule. Are the 2 sides the same? No, they're different. And what else do I have attached here? A hydrogen. So do I have 4 different things attached to that carbon? Yes, I do. Yes, I do. Okay, go down to the next carbon. I have a hydroxyl. I have the rest of the molecule going this way. I have the rest of the molecule going this way. Is it the same? No, it's different. And what's my 4th thing that's attached to it? Hydrogen. So chiral or achiral? It is chiral. How about my next carbon? Same thing, right? I have a hydroxyl, part of the ring, and a hydrogen. So chiral or achiral? Chiral. How about this carbon? Same thing, right? I have a hydroxyl, I have this portion of the ring, I have that portion of the ring, and I have a hydrogen. So chiral or achiral? Chiral. So how many chiral centers do I have? Yeah. So that's glucose. We're gonna really get to know glucose in chapter 6, I do believe. Okay, can oxygen be chiral? No. So move on. Carbon. Is this carbon chiral? Why is it achiral? It is, you are correct, it is achiral. There's 2 hydrogens on it. So can't do it. Okay, how about this next carbon right here? Chiral or achiral? Achiral, why? It has two methyl groups attached to it. The methyl groups are the same, so they are, that one carbon is achiral. How about this methyl? It is achiral, because what is a methyl group, right? It's bound to a carbon, and then it has what attached to it? 3 hydrogens. Are hydrogens the same? Yeah, so can it be chiral? No, so neither one can be chiral, right? Okay, go on to the next one. Chiral or achiral? Chiral. It is absolutely chiral. It has a hydroxyl. It has this R group, which is different than this R group, and it has a hydrogen. So it's chiral. How about this carbon? None of the groups attached to it are the same, but what's the problem? Is it tetrahedral? No, because it only has 3 bonds. Well, it really has 4 bonds, but it only has 3 areas of electron density, right? So you have a double bond. Anything with a double bond, immediately exit out. Anything with a triple bond, immediately exit out. Okay, nitrogen. No. Next carbon, chiral or achiral? Achiral. Chiral or achiral? Achiral. Chiral or achiral? Achiral. How many chiral centers? Once you know what you're looking for, it's not bad. Right, here's an example of an antibiotic. If I start with this carbon, chiral or achiral? Achiral. Tell me about this functional group. What is this functional group? So an aromatic or a benzene ring, you are studying your functional groups, correct? You saw the Quizlets I posted that other people in the class have made. If you want to share your own and be nice to the class, you're welcome to do that. So what do we notice about every single carbon in an aromatic ring? It's participating, every single carbon is participating in a double bond. So can they be chiral? No. So anything, I'm looking here, anything that's participating in a double bond, what am I going to automatically go in and do? Exit out. Anything that's a methyl group, I'm going to automatically go in and X out. Anything that only has 2 bonds, because what does that tell me? It's got 2 hydrogens. So I have to X that out. Okay, what have I got left? I have 1 carbon here, chiral or achiral? It is chiral because we have an NH2 group, an aromatic, and then the rest of the molecule, and then it's got a hydrogen. So it's absolutely chiral. Nitrogen can't be one. How about this one? It is chiral. It is chiral because you're bound to basically all of this junk. And then you go this way on the ring, and then you go that way on the ring, and you got a hydrogen. Okay, last carbon right here. Chiral or achiral? Chiral. Once you go in and eliminate those double bonds, eliminate anything that only has 2 bonds, eliminate methyls, you're kind of done. Okay, so you do this molecule real quick and tell me how many chiral centers. How many chiral centers? None. None. This is a double bond. Oh, I was doing it in red. Be consistent. This is participating in a double bond. This carbon only has 2 things attached to it. This carbon has only 2 things attached to it, and those are the only carbons. 0 chiral centers. Cool. All right. Okay, that is the end of chapter 4. How do you feel about that? Pretty awesome, right? I feel I feel like we should be accomplished. We should feel very accomplished right now. All right, so the next thing that we're going to talk about is diving deeper into chemical reactions, right? We've kind of talked about chemical reactions very, very, very generally. And so what we're going to do is we're going to talk about them in a little bit more detail. And when we talk about chemical reactions, there are a couple of different parameters of any given chemical reaction that are really important. And we call a lot of these parameters thermodynamics. So I want to talk about all of those parameters before we get into questions about it, right? So the first one has to do with the name thermodynamics. What does thermo refer to? Heat, temperature, right? Okay, so you've heard of something that can be endothermic, right? And you've heard of something that can be exothermic. You heard of that before? So anytime you hear thermic, what should you be thinking? Heat, temperature, right? So when we talk about things that are endothermic or exothermic, the symbol that we use is H. And we don't talk about its temperature because that doesn't really give us any information. Remember, all of our chemical reactions are reactants going to products, right? So we have a change happening. So we don't really care what the temperature is. We care, did the temperature go up or did the temperature go down? So in order to look at that, we look at the change in, what's the symbol for that in science? Delta. So we look at delta H. Delta H, the change in heat can be either positive or it can be negative, right? So if you have something that is endothermic, that's telling you that heat is entering the system, right? So we call that a positive delta H. If we have something that is exothermic, what is heat doing? Leaving, like exit, right? That's what I think, exothermic and exit. So delta H is going to be negative, right? So that's one parameter that we kind of look at. Then the second parameter that we talk about is energy. And the energy that we talk about is Gibbs free energy. So instead of using the letter E, we use the letter G for Gibbs. And we call it, if energy is leaving or entering a system, we talk about endergonic and exergonic. And at the same time, we don't care how much energy is in the system. We care the change in it when we go from reactants to products. So we're again going to look at that delta symbol, that change in energy. So if something is endergonic, what do you think the sign is going to be on delta G? Positive. If something is exergonic, what's the sign going to be? Negative. Okay. The next thing that we look at is we look at the amount of disorder in a system. And so we call that entropy. And our symbol for entropy is S. And we're not going to look at the absolute value. What are we looking at? Change. Another word for entropy is disorder. So if we have something that has randomness, right? That's what, when you think of disorder, I think of random, right? Disorder, randomness. Randomness. So if you have something that becomes more random, what is my sign going to be on delta S? It's going to be positive. If I have something that becomes less random, negative. Look on your best friend. Is this on your best friend? It's not. It's not on your best friend. What do you do with stuff that's not on your best friend? You memorize it, but you don't just memorize it. This is my advice. I like to give exam advice at random times in the semester. when you get your exam, go to a blank space, go to a space on, because I'm going to staple your best friend to your exam. Go to a place on your best friend that you have some space and write this stuff down. Because when you get to a question, how often do you get to a question that has all this different vocabulary and you get confused? It happens all the time, right? English is the same, science as a second language. It's a lot of crazy terms, but if you have it written down ahead of time, you're not going to get confused. So this is absolutely something that I would like, before I even answer my first question on the exam, I would write this down. Okay, it's just good advice. Okay, I did 5.1 in the video, right? I did the odd numbers. No, I didn't. I skipped it. Okay. All right. So when vinegar and baking soda are combined, the mixture spontaneously undergoes an endothermic reaction while releasing CO2 gas. Would the test tube feel hot or cold? What did it tell us in this reaction? Let's answer it one at a time. It is endothermic. So what is that telling me about what heat is doing if it is endothermic? Heat is entering the system. So is it going to get hotter or colder? If something is hot, it's giving off heat. If something feels cold, it feels cold because it's sucking the heat out of you, right? So if I hold on to a test tube that's undergoing an endothermic reaction, I am not the system. The test tube is the system. The test tube is going to suck my heat into the reaction to fuel the reaction. So the test tube is going to feel cold, right? So the test tube is going to feel cold because, we'll say because heat enters the test tube. Because you could say heat leaves your hand. If I could scroll up and be able to actually write, right? Heat leaves your hand and enters the test tube. The test tube itself, this is the system. So the system is absorbing the heat. So the surroundings feel cold, right? Your hand is the surroundings. Does that make sense? It almost feels backwards, but it's not. Okay, do you think this reaction would have a positive or a negative value for delta G? Explain your reasoning. So when we talk about spontaneity, right? I want you to picture me on a bicycle, all right? Now, there are two different things that could happen. I am at the top of a hill on a bicycle. What is going to happen? If I pick up my feet, what happens? I'm going down, right? Spontaneously. Do I have to put energy in? Oh no, that is going to be a fun ride, right? That is spontaneous. What happens if I'm at the bottom of the hill? Oh my gosh, I have to put energy in. I am going to have to pedal, and y'all are just going to sit on the side and laugh at me as I struggle to pedal up the hill, right? Okay, so if something is spontaneous, do you have to put energy into it? No. So what does putting energy in mean? Energy in is positive delta G. Energy out is negative. So negative delta G is something that is spontaneous. So a negative delta G is spontaneous. Right? Remember we talked about this with kinetic and potential energy? Me sitting at the top of that hill, I have lots of potential energy, and as I go down, it gets converted into kinetic energy. So I'm giving off kinetic energy. It's the same thing in a chemical reaction. If I'm giving off energy, I have a negative delta G, and I am spontaneous, right? Like rust. Rusting is a spontaneous reaction. So it would have a negative delta G, right? It's spontaneous. It's happening on its own. You don't have to put energy in to make your car rust. You just leave it for long enough, right? Okay. All right. In your own words, define free energy change delta G. So when I asked you if I was, what would happen to me if I was sitting at the top of the hill or the bottom of the hill, right? What I'm really asking you about is the amount of energy that's available to do work, right? This is why we have lunch, have dinner, right? So that we have energy that is available to do work. So in a chemical system, in a biological system, in a physical system, doesn't matter. You really have to know what an organism can do is just what free energy is available to do work. So that's what delta G is. Delta G is the free energy available to do work. Okay. All right, now A, how does delta G differ in exergonic and endergonic reactions? In exergonic, what do we know about that? Delta G is what? If something is exergonic, it's giving off energy, right? So it's negative. If you are endergonic, energy has to enter the system in order for you to have your chemical reaction go. So it must be a positive delta G. Do you see how nice it is to write this out in the beginning? To be able to come back to it? That's what you want to have for your exam. Okay, which is spontaneous? A reaction with a positive or negative value for delta G? Negative. Like, how much easier was it to answer those questions with that cheat sheet right there, right? Okay. Oh yeah, I did that. Okay. Classify the following as exergonic or endergonic reactions. Okay. On a reaction energy diagram, the reactants show lower energy than the products. So here's an energy diagram. We go always in chemical reactions from reactants to products. And so this is an energy diagram. So what I'm graphing on my other axis is Gibbs free energy. I always want to put delta G, free energy. Okay, so this is saying that my reactants are low and my products are basically high, right? That's what this statement is saying. So I'm going to put my reactants low and I'm going to put my products up high. We agree with that? All right, so technically a reaction diagram looks like this. It's got a little hump, but I'll explain that later, but I don't want to draw one without one because then you're going to be like, well, why'd you add that later? But think about this, right? Tell me about delta G for this. It's going to be a later question, but I want to do it right now. Tell me about delta G. If I started off low and I went high, tell me about delta G. What kind of a reaction do I have? Well, a positive or negative? Positive. I have to, this is me at the bottom of the hill. Oh my gosh, let's see if I can draw me. And I'm so sad. This is how great of an artist I am. I can't even draw a bike. I'm really sad because I'm at the bottom of the hill, right? I'm going to have to put a ton of energy in order to get to the top of the hill. So my delta G value is going to be positive. If you have to draw a little stick figure of me to make it work for you in your mind, go ahead and do it. It's all good. Okay. So I have a positive delta G. Am I exergonic or endergonic? Endergonic. Y'all with me on this? All right, so let's do the next one. On a reaction energy diagram, so here's another one. The products, so we're going from reactants to products. The products are low and the reactants are high, right? That's the way to do that. So reactants to products. So my products are low, my reactants are high. So technically there's a little bump and then it goes down. But we'll talk about the little bump later. Am I on my bike? I'm at the top of the hill. Am I happy or am I sad? I am so happy. It's hard to draw, but I'm so happy. It's hard to tell right there, but I'm very happy, right? Do I have to put energy in to get to the bottom of the hill? No, I'm actually going to give off energy. So what energy is leaving the system? So what's my sign on delta G? Negative. Am I endergonic or exergonic? Okay. Not too bad, right? And the next one, I think it says go back to 5.4 and give the sign of delta G, but we already did that, right? We're good. Okay, so now we're going to talk about delta S, our entropy, right? So what is delta S? Remind me? It's randomness, right? Randomness. So let me ask you something. When you decorate your Christmas tree at Christmas, right? How do you pick up your lights when you're done? You just like throw them in the box? No, I don't do that. That like hurts me a little bit. I like to take them, I like to wrap them around cardboard, right? And tape the two ends so that when I pick it up, you know, it stays together and it doesn't get all in that jumbled mess. So which one has more entropy? If I just throw it in the box or if I wrap it around that cardboard? Throw it in the box has way more entropy, right? And have you heard this term before? The universe tends towards disorder. You've never heard that before? So it's a really common sciencey statement, and a lot of times people have a really hard time understanding it. But how many different ways could that string of lights be arranged in the box if you just threw it in the box? How many different possibilities are there? Oh, a crap ton, right? A ton. But how many different ways can you wrap it around that cardboard? Only a few, right? So there are more possibilities for disorder than there are for order. And so that's why you hear that. Same thing with like a deck of cards, right? How many different ways can you organize a deck of cards? Really one way, right? But when you shuffle, how many different possibilities could you get every time you shuffle? A ton, right? Okay, that's the same thing. It's way more disorder when you're shuffled than when you organize the cards. So that's what you can just kind of have to think about. Are you becoming more random or are you becoming less random when you look at these chemical reactions? So look at A, liquid gasoline burning to form carbon dioxide and steam. Liquid gasoline. What state of matter is that? It's a liquid. It's going to burn and it's going to form carbon dioxide and steam. What state of matter is that? What is more disordered? A gas, right? So that's part of it. What I'm not telling you is gas, right, is a really big hydrocarbon, right? A really long chain hydrocarbon, lots of carbons, lots of hydrogens attached in these really big molecules. How big is carbon dioxide? CO2. How big is steam? H2O. They're really small molecules. So you go from really big molecules that are close together in the liquid form to really small molecules that are in the gaseous form and all over the place, right? So what happened to disorder? Oh my goodness, going this way, you got more disorder, right? So what do we say for delta S? Positive, you got more disordered. So this is A. Okay, B, cleaning up your bedroom. What were your reactants in this process? Your room, right? Your room's the reactant. How was it at the very beginning? It was a mess. It was like my son's bedroom currently. and always, even when he says he cleans it. All right, so we go from a mess to being clean. What happened as I go this way with my disorder? Did I get more disordered or less disordered? Less disorder. What's my sign on delta S? Isn't this easy? If you think about it this way, it's easy. Okay, C. Oh, this is a fun one. A stick of dynamite exploding. Just think about it real quick. A stick of dynamite. And is what state of matter? A solid. What happens when it explodes? What does it turn into? Gas. And dynamite is another one of those really big molecules that then gets broken down into tons of really small ones. And so you have that in addition to it. So as I go this way, what happens to my disorder? More disorder. What's my sign on delta S? That's why explosions are insanely dangerous, because you have so much energy inside of them, right? It's so amazing and cool. What chemist doesn't like an explosion, right? Wouldn't be a good chemist. Okay. Classify the following as spontaneous or non-spontaneous. Do you remember what that refers to? Delta G. So walking on a treadmill at the gym. If I'm at the gym, if I want to walk on a treadmill, is it going to happen on its own? No, I have to put energy in. That's the whole point of going, get on the treadmill, right? To expend the energy. So walking on a treadmill is going to be non-spontaneous. A chemical reaction that requires free energy. If I have to put energy in to make the reaction go, is it spontaneous? No, this is another non-spontaneous process, right? So you can think about it in real life and you can think about it in chemistry. It's the same thing. So if you can relate it to an everyday event, it's going to be a lot easier. Okay. So the last thing in this section is talking about the energy that's stored inside of our food, right? And we know there are different ways to measure that kind of energy. How do we measure it nutritionally? Big C calories, and that's nutritional. Then we have what? The little c calories, and that's chemistry. And then what's the other way to measure energy? Joules or kilojoules, right? Either way, but both of those are chemistry ways to define energy. So the things that we eat each have a different amount of energy inside of them, right? This is really important for some people, especially those people who are diabetic, right? What do diabetics have to do? Watch their sugars, but not only watch them, they actually count their sugars. They count the amount of calories that they get from sugar, because they have to know exactly how much sugar is going into their bloodstream so that they give themselves the right amount of insulin in order to tell the cells, hey, you could take that sugar into the cells and use it. Otherwise, what happens? They have massively high blood sugars, and that's very, very dangerous for extended periods of time, right? And so what we're going to do is we're going to look at each of the different types of food, carbs, proteins, and fats, and each one has a different energy component to it, right? They each cost a different amount of energy. And we'll see how much energy is in, I think it's breakfast. Next time we'll see you, right? So have a good breakfast next Tuesday, because we're going to talk about breakfast, and you're going to be wanting a good breakfast if you haven't. Y'all have a great weekend. Okay, anybody? Oh, I took down my chat. Anybody on chat need anything? All right, come on, go ahead and end the Zoom.